Nanotechnology and a new scientific era. 1. Display elements. 2. What is nanotechnology? 3. The history of nanotechnology. 4. Methods for preparing nanometric materials. 5. Nanotechnology applications. 6. Nanotechnology obstacles. 7. The risks of nanotechnology. Nano, symbol N, is a unit prefix meaning 1/1,000,000th. Used primarily with the metric system, this prefix denotes a factor of 10⁻⁹ or 0.000000001. It is frequently encountered in science and electronics for prefixing units of time and length. Nanotechnology is a field of research and innovation concerned with building things, generally materials and devices, on the scale of atoms and molecules. How small is nanoscale small? Well, it's so tiny that it might take a moment to get your head around. To reach the nanoworld you have to go smaller again. A nanometer is 10 to the power of 9 meters, which is 1,000th of a micrometer, or 1/1,000,000th of a meter. This is the scale at which we measure atoms and the molecules they make. The history of nanotechnology. It is not possible to specify a specific era for the use of this technique, as it was mentioned that glassmakers in the Middle Ages used colloidal gold nanoparticles to color the glass, and this is supported by the Roman king Lycurgus Cup. In 1959, the famous American physicist Richard Feynman spoke in a lecture under the title, "There is a wide space at the bottom," in which he explained that matter at the infinitesimal levels, now nanoparticles. In 1986, the American mathematician Eric Drexler, the actual founder of this science, wrote a book called Genesis Engines, in which he laid out the basic ideas of nanoscience. In 1991, a new physical phenomenon was discovered for the first time, which is nanotubes at NEC Electronic Industries in Japan by the scientist Sumio Lijima. In 2003, the secrets of this technology have been recognized and the world of nanomaterials was controlled. In 2004, the stage of industrial applications of this technology has begun, when nanomaterials were used in the Malaysian rubber industry, and the results were amazing. The mechanical properties of rubber jumped from 12 to 20 times by adding simple parts of nanomaterials. There are many methods of manufacturing nanomaterials that have been divided into two main parts. One of them is from top to bottom. As for the second method, it starts from bottom to top. Nanoparticle synthesis refers to methods for creating nanoparticles. Nanoparticles can be derived from larger molecules, or synthesized by bottom-up methods that, for example, nucleate and grow particles from fine molecular distributions in liquid or vapor phase. Synthesis can also include functionalization by conjugation to bioactive molecules. Synthesis of nanomaterials in high yield and low cost has been a great challenge since the very early development of nanoscience. Application of the nanoparticles in medicine depends on the ability to synthesize particles with different shape, monodispersity, chemical composition, and size. Traditional lithography. 1. Graining the stone. Firstly, oil patch cleaner is applied to the stone, and then scrubbed thoroughly with a scourer. 3 grades of carborundum grit are then used, coarse, medium and fine. 2. Drawing on the stone. When the drawing is finished, it is then dusted with French chalk. This helps to protect it during processing. 3. Processing the stone. The stone is processed using gum arabic, sometimes with a very small amount of nitric acid added. The purpose of the gum is to chemically separate the image and the non-image areas, so that the greasy image areas become water repellent or hydrophobic, and the non-image areas become water receptive or hydrophilic, so that when printed, only the image areas receive the ink and print. 4. Washing out and rolling up. 5. Printing the stone. What is lithography? Lithography is the transfer of geometric shapes on a mask to a smooth surface. In modern semiconductor manufacturing, photolithography uses optical radiation to image the mask on a silicon wafer using photoresist layers. Other methods are electron beam, scanning probe, X-ray and XUV lithography. Steps used in photolithography. 1. Surface cleaning. 2. Barrier layer formation, oxidation. 3. Spin coating with photoresist. 4. Soft baking. 5. Mask alignment. 6. Exposure. 7. Development. 8. Hard baking. 9. Post-process cleaning. Micro and nanolithography technology have been utilized for decades to fabricate integrated circuits. This technique can create patterns with size in the nanometer range. Lithography is usually combined with deposition and etching to yield high-resolution topography. Lithography can be divided into masked lithography and maskless lithography. In masked lithography, masks or molds will be used to fabricate patterns. The types of masked lithography include photolithography, soft lithography, and nanoimprint lithography. Maskless lithography yields arbitrary patterns without the use of masks. For example, electron beam lithography, focused ion beam lithography, and scanning probe lithography. In nanospheric lithography, a set of required nanospheric films on a surface is used as a mask. The nanostructures are dispersed into a liquid, known as a colloid. Depending on the surface properties and the type of media used in the colloid, the nanosphere will self-assemble into an ordered pattern. There will be an empty space between the two nanospheres, which is repeated regularly in the whole surface, and this space is usually used for the relatively flat nanotype box on the surface, to use the pattern of the nanosphere as a mask, and a substance such as gold or silver is sprayed on it, after removing the nanosphere, leaving a regular pattern of points. The chemical vapor deposition process uses hydrocarbons as the carbon sources, including methane, carbon monoxide and acetylene. The hydrocarbons flow through the quartz tube, being in an oven at a high temperature, 720 Celsius. Schematic diagram of the chemical vapor deposition apparatus. At high temperature, the hydrocarbons are broken to be the hydrogen-carbon bond, producing pure carbon molecules. Then, the carbon will diffuse toward the substrate, which is heated and coated with a catalyst where it will bind. Carbon nanotubes will be formed if the proper parameters are maintained. The advantages of the chemical vapor deposition process were low power input, lower temperature range, relatively high purity. Plasma arcing. Plasma bending is the most common method for fabricating nanotubes. In this method we use a plasma coil, which is an ionized gas. Then we applied a potential difference between two electrodes and a gas between ionization. The electrode, anode, evaporates when electrons are taken from it. For example, a carbon electrode is used to produce carbon nanotubes. This electrode is consumed during the reaction to produce carbon cations, and these positive changes the ions pass to the other electrode, to capture electrons and deposit them to form nanotubes. This method is also used to deposit nanostructures on surfaces, but it should be 1 nanometer thick. It is considered a nanomaterial. The colloidal solution process is carried out in the liquid phase, and can be used to fabricate such nanoparticles as well as surfaces with nanostructures or three-dimension materials. A colloidal solution is a chemical mixture in which particles of a single substance are suspended in a mixture. The first stage of the process is the synthesis of colloidal matter. This colloidal suspension develops network formation in a process called formation and network formation in a continuous liquid. The first stage is the hydrolysis reaction, using a catalyst, which can be a base or an acid, for hydrolysis to begin to condense and polymerize. Depending on some conditions such as pH, it can reach dimensions of a few nanometers. Then the particles agglomerate, and the mesh in it begins to form throughout the liquid medium, which forms a gel. Applications of nanotechnology. 1. Electronics. 2. Medicine. 3. Molecular manufacturing. 4. Renewable energy. 5. Paint manufacturing process. 6. Physical processes. 7. Optics. 8. Biotechnology. 9. Catalyst manufacturing. 10. Production classification system. Risks to humans. We already knew how small the nanoparticles are. It may be surprising that they have a dangerous effect on the human body, but despite the beneficial features of these particles, any particle of 300 nanometers has the ability to enter the human body easily and without any resistance based on their small size, as it can spread and cause damage in the body, and a particle of 70 nanometers can enter the cell nucleus. Some studies have been conducted on animals in the laboratory, and have shown that when the particles enter the human body, they collect in the brain, blood cells and nerves, which means that it is possible to classify these particles among the destructive substances of the human body. Risks to the environment. Example, biological accumulation, which arises from the accumulation of unwanted nanomaterials, and the other in its small size, which will be difficult to detect, clean and remove from the environment. Nanotechnology obstructions. The difficulty of this technique lies in obtaining accurate measurements when reaching the level of an atom. It's also considered difficult to control the atoms after the fragmentation of the substances that are made from them, so the atom becomes unstable and turbulent as a result of the difference in its natural position. Design: Osama Basel Adnan Yuns, Musa Ibrahim Al-Flat, Ayman Khalid Ramadan Al-Arag.